Alright guys, just finished with football, and of course I couldn't video for you fourth period because you guys were in here taking Math 171. Hope you guys enjoyed that, and we'll see you again tomorrow. Alright, types of graphs. There are two main types of graphs we use when describing motion in physics. The first type is the DT graph, or displacement versus time graph. D stands for displacement, or T stands for time. The other type you'll sometimes use is the VT, or velocity versus time graph. So the V stands for velocity, T stands for time. Now, when we look at DT graphs, these are the more commonly used to describe motion. A lot of it is because it's a lot easier to just graph out the displacement than it is to try to figure out the velocity and graph that out each time. You can do both. And when you get into calculus next semester, possibly this, depending on how far your guy goes, you can actually start seeing the relationship between DT and VT graphs. So, looking at DT graphs, there's some things that the graph can automatically tell us. The first is if it's linear, so the whole graph is a straight line, the velocity is constant. It does not change. So think about this, and later on I'll point this out again. Slope is velocity for a DT graph. So if the line is straight, slope's not changing, velocity's not changing. Now, same thing. If you look at a DT graph and it's not linear but it's parabolic, we'll show you that later, it is constant acceleration, or it is showing acceleration. If there's any curvature at all to the line, there's acceleration. The degree of curvature tells us how much acceleration there is. Now, here we go with slope. The slope of the line at any given point is equal to the velocity at that point. So if the line is curved, we can figure out the slope of that point, and that is the velocity at that point in that instant. Now, to figure out the average velocity, it's real easy. You draw a straight line from the start of the graph to the end of the graph. Figure out the slope. There's your average velocity. That simple. So let's actually look at some graphs and kind of figure out what's going on. So, looking at this, it's a DT graph. Again, if we look at it, it's straight. So to figure out the acceleration at any point, we just got to find the slope. Now, because it's a straight line, is our slope changing at all? Not really. Actually, not at all. So we don't have to do a lot of figuring out, okay, what's the slope at this point, what's the slope at this point, what's the slope at this point. It's constant. So our velocity is constant. And again, if we remember what slope is equal to the rise over the run. Now, because it's a straight line, this one's really easy. You can find any points that you definitely know the numbers and figure out your slope from that. So for example, I know down here at 0, it's 0, 0. Then I'm going to go up, and I'm going to go all the way up to 8, because that's my next time I hit a whole number. And there we go. So my rise is 8, my run is 5. So my slope is 8 over 5. So 8/5, which works out to be 1.6. So my velocity here is 1.6 meters per second. Or I could have done the big long slope and gone all the way up to the top and all the way over, which would give me 16 over 10, 1.6. Or you can also, let's get this up here. Oh, wow. Come on. Here we go. One more. There. Now, we can also just do math with this. So if I ask you what the average velocity is, you don't even have to really do much since we start at 0, 0. You just figure out the farthest distance we went to, which you look up here, farthest distance was 16, which took 10 seconds. 16 meters divided by 10 seconds, there we go, 1.6 meters per second. Piece of cake. Constant velocity is very easy to work with. Where it gets a little bit harder is when we have a curve. We see that this line curves, right? Well, we should see if we are actually looking at it. So we don't have constant velocity. This is one of those cases where we know we have acceleration because the line's curving. There are several things we can get from this line. So we look at it and we can kind of look, hey, I know the acceleration is going up because my slope is getting steeper each section. Now, I'm not going to find any sort of linear relationship with this, so I can't, like on this one, I could have found the line of best fit, used the y equals mx plus b formula to figure out my y-intercept, to figure out my slope, to figure out what my final value is going to be. It gives me a lot that I can do with it. Too far. There we go. Let's not go too crazy after football. This one, line of best fit, doesn't do anything for me. So I'm going to have to do something else. So this one, it's a bit harder to figure out your final value because you guys really aren't at the level mathematically where you can find a parabolic line of best fit effectively every time. If you're in Excel, Excel will do it for you. You can use it to predict the future using Excel. You're not going to have that option on any sort of test, so I'm not going to expect that of you. Now, some things here. If we look at it, focus right here. The slope of the line at any given point is equal to the velocity of the line at that point. So one of the things you're going to probably hit some point in calculus, I don't know where, I just remember it vaguely from my calculus, is doing tangent lines to a curve. So for example, if I wanted to know what the slope or what the velocity is at 4 meters, I could figure out a tangent line, that's the line that only touches it right there. And if I could draw a straight line, the slope with that tangent line would tell me the acceleration right at that instant. I'm not going to expect you to do that. I do expect you to know that that relationship is there. So you have to know the concept. I'm not going to actually expect you to figure out, hey, what's the tangent line, what's the slope of the tangent line, yada, yada, yada. Yeah, I'm not going to do that. At least I'm not going to do that without first teaching you how using computer and or calculator. Which means I'm not going to do it because, yeah. Now, looking at this, it's really straightforward. So now we're going to go to the other types of graphs, your VT graphs. These you only really use if you have definite data for your velocity, because it's really hard to get good velocity numbers if you don't have something to actually collect them. Now, if you actually collect velocity versus displacement, you can do some great VT graphs. And if you have a good VT graph, you can actually go back and do good DT graph. Now, if I have a good DT, I can also figure out my VT. Yeah, it gets really complicated. I'm going to shut up now before I confuse you more. These are less common because it's hard to get good velocity data. If the graph is linear, hey, straight line, acceleration is constant. So your acceleration is not changing. If it's not linear, your acceleration is not constant. It's that simple. Linear, constant acceleration. Not linear, not constant. Now, looking at this, it's very similar to dt because the slope tells us something. But where the dt told us the velocity, the vt, like this one, is going to tell us acceleration at that point. Now, if it's linear, all of these will have the exact same slope, which means my acceleration throughout is not changing. Now, there's one other thing we do here, which you'll again probably do somewhere in calculus, is we look at the area under the curve. So I can figure out what my position is, or what my displacement is, by looking at the area under the curve. So the easiest way to kind of cheat with this is we take these numbers, so 0 and whatever number that's going to be, and we average them. And then we multiply them by 1 because that's our width. So it's 1 and let's call that 1.6, which gives us 0.8. So 0.8 times 1 gives us 0.8. So after 1 second, our displacement should be 0.8. And that's looking at this area, the area under the curve. Now, what if I want to know my position at 2? Well, if I'm going 0 to 2, I look at this whole area. So if I was wanting to know my position from 0 to how far my displacement was from 0 seconds to 2 seconds, I would take 0, then I'd come over here, and I'd see that's about 3.2, and then I'd go in and do 1/2 3.2 times 2, which would give me 3.2. So from 0 to 2 seconds, my displacement is 3.2 meters. Now, it gets harder if it's not always from 0, because we have to start doing some subtraction. So let's get rid of this and let me show you exactly what I mean. So what if I want to know what my displacement is from 3 seconds to 4 seconds? Well, I start at 3 seconds, so I'd have to go up, go over, go down, and this is the area I'm looking for. So this is the area under the curve from 3 to 4. So I got to figure out my value at 3, which is going to be 4.8, and then 6.4 it looks like. I'd average them out, multiply by 1, and that'd give me my area under the curve. With straight lines, it's really easy. Where this gets harder, and you'll probably have to do this more in calculus than you'll ever have to do in here, is where you have curved lines. In here, I don't care about curved lines because we only deal with constant acceleration for making you find displacement. So, piece of cake, right? Good. We'll pick up more tomorrow in class.